Hello, we are continuing our video series on Chapter 3, Section 1. We're looking at sampling distribution. And sample size is very important. So as the sample size increases, the variability of the sample statistics tend to decrease, and the sample statistics tend to be closer to the true value of the population parameter. So for larger sample size, you get less variability in the statistics, so you get less uncertainty. So let's go back to the example looking at Reese's Pieces. I'm going to go to the example we did a couple videos ago. So here, notice we looked at sample size 10 if we're grabbing 10 Reese's Pieces at a time. And notice the standard error is 0.156. This standard error is the standard deviation of the sample distribution. So keep in mind here are a bunch of dots, 1,248 dots, and each dot represents one sample of 10 Reese's Pieces. So we get a standard error of 0.156. So I'm going to reset this. Get rid of that. And let's say we take a sample size instead of 10, let's change that to 30. So that means instead of taking 10 Reese's Pieces, we're going to take 30 Reese's Pieces. So we have one sample right here, 14 out of 30 Reese's Pieces is 0.467. Plot that right here. Take another one. We'll get the same exact proportion. P hat would be 14 over 30. Another sample. I just took 8 samples right here, and our largest value we got 20 out of 30, or 0.67. All right, let's take, I want to get the same amount. So now we've got 48 samples right here in our dot plot. And if you remember from 2 videos ago, we're looking at this, that we got actually 0.8 out of 10. But here our biggest value we have so far is 0.7. All right, I'm going to go ahead and generate 1,000 samples. That's the same. I got 1,248 samples of size 30. So each of these dots on here, we have dots. That's a little bigger. Each of these dots represents one sample of 30. We did get a couple 0.8s here and a 0.2, 6 out of 30. But notice that standard error, that standard deviation is a lot smaller. Before it was 0.15 and now it's 0.08. And that is because we took a bigger sample size in this case. So that would be what we looked right here, changing that sample size n changes the variability. So suppose we take samples of size 10 and samples of size 100 from the same population. And we're going to compute sample means this time instead of proportions. Which sample mean would have the higher standard error? All right, hopefully you picked A, 10. If we take a smaller sample size, and remember we're taking many samples of size 10, but a smaller sample size gives more variability. So we get a higher standard deviation. One way to think about this, if you were to take, say, height, if we're looking at sample means, we take height. If we take a sample of size 10 and we happen to get the center of a basketball team who's 7 foot tall, that's going to throw off the average of these 10. If you have 9 kind of people around, 5, 6 feet, and then you throw one 7-footer, that sample mean is going to be pretty high. But if you get that same 7-footer in a sample size of 100, then you have 99 other people that are going to kind of take that average down. So that helps me kind of keep this in mind. If I have a small sample size, outliers will affect the statistic much more than if you have a much bigger sample size. Oh, yeah, the question, suppose we take a sample of size 10, a sample size of 100, from the same population, and we're going to compute the sample mean. Which sample mean would have higher uncertainty? Well, hopefully you picked A, because essentially this is the same question as before. Higher standard deviation is the same thing as a higher standard error, which is the same thing as higher uncertainty when we're looking at sampling distributions. All right, we've got a sampling distribution for enrollment in a statistics grad schools. One dot, so this is a sampling distribution. What does each one dot represent? Enrollment at one statistics grad program, one sample mean, 1,000 different enrollments, or 1,000 sample means. Well, we're looking at a sampling distribution. So each dot represents one statistic from one sample. So we get B. Each dot represents one sample mean. There's lots and lots of different sample means displayed in the sampling distribution dot plot. All right, now we're looking at the sampling distribution. Is shown for enrollment of statistics graduate schools, and the population parameter is closest to. And help you pick D, 55, because the mean of all these sample means is about 53.433, which is closest to 55. So the center of the distribution is going to be the best approximation for the population parameter. All right, same dot plot. What is the standard error? All right, the answer to that is B. Okay, 10. This one's a little trickier. So we're taking the middle 90% of the data, appears to extend 20 out on either side. So I look at this, and I'd try to, where would the cutoff be to where I get about 95% of the data? Probably around here, maybe 35 or so, all the way to here, maybe about 75. So if we imagine this taking 35 to 75, that cuts off the middle 95%. The difference between 35 and 75 is 40. But remember that 95% is contained by 2 standard deviations above and below. So 35 to 75 would be 4 standard deviations. So if we take 40, the difference between 35 and 75, and divide that by 4, we get 10. Or another way to think about it is I need to subtract about 20 from 53 to get to this lower cutoff, and then we cut that in half to get 10. Okay, random samples are taken from a population with mean mu. That's our parameter. And the sample means are shown in the dot plots below. What would we estimate from these two dot plots that the population parameter mu is? And the answer, 25. To get the population parameter, it should be about the center of the dot plots, which it is, about 25. Okay, one of these dot plots comes from a sampling distribution of size 50, and the other is computed from a sample size of 200. So for the dot plots, each dot represents a mean of 50, size 50, or 200. So part A, does the sample size 50 go for C1 and the 200 go for C2? Does the 200 go for C1 and the 50 for C2? Or is it impossible to tell? I'll give you a hint. Think before we talked about how the bigger the sample size, the less the variability. So the answer is B. If we have a bigger sample size, each of these dots in C1 represents a mean gathered from a sample of 200, but those means as a distribution are going to be much more compact and less variable than if we take a smaller sample size of 50. Remember, smaller sample size means if we take even one outlier in that sample, it's going to have a much bigger effect. Now we're looking at C2, the bottom dot plot. What would you guess the standard error is for the sampling distribution? And the answer is A, 5. If we look at the bottom graph, if I want to cut off the middle 95%, looks like it's around 15 all the way to 35. So somewhere around here, we would get that 95%. And if I think about the small end, 25 would be the middle to 15 would be 10, moving over a distance of 10, 25 to 15. But that would be 2 standard deviations. So if we divide that by 2, we get 5. All right, same question, but now we're looking at the top graph, C1. What would the standard error for the sampling distribution be? This one might be hard to see, but we're going to say the answer is 1. Because if I'm looking at the top graph, if I just move over 1, or if I move over 2, if I move over 2 on each side, that looks like that's going to get me about 95% of the data. 2 down and 2 up. And then we need to cut that in half to get our standard error, which is the standard deviation of the sampling distribution. Okay, here we have samples of size 5 are taken from a large population. And we know the population mean is 8. We know the parameter is 8. And the sampling distributions for the sample means are shown below. We have dataset A on top, dataset B on bottom. We want to know which of these used random sampling. And the answer for that is B. Why is that? If we're doing true random sampling, and our samples are random and represent the population, the center of the sampling distribution should be about the same as the population parameter. So part B, the center is somewhat around 8, whereas dataset A, it looks like the center is going to be closer to 5. So going off the same 2 graphs, dataset A is on top, dataset B is on bottom. Again, we know the population parameter is 8. The sampling method for A is unbiased, biased high, or biased low. And the answer for that is biased low. The center of A is biased, and it looks like the population means around 5, which is significantly less than 8, the true population parameter. All right, in conclusion, in this section 3.1, we talked about statistical inference, drawing conclusions about a population based on a sample. We used a sample statistic to estimate a population parameter. To assess the uncertainty of a statistic, we need to know how much it varies from sample to sample. And to create a sampling distribution, we take many samples of the same size from the population and compute the statistic for each. And the standard error is the standard deviation of the statistic. Thank you.